So that, if you like, is our landscape of isotopes, just for the bottom part of the periodic table, these elements of hydrogen through beryllium. But at the moment, it's kind of a flat landscape. There's one other thing that you really need to understand before we can go on and discuss rare isotopes. There's nothing in here which indicates which isotope is regular and which isotope is rare. The fact is, I talked about the strong forces that bind the nuclei together, but there's another force called the weak force. It's a hell of a lot weaker than the strong force, but over time, what this can do, it can convert a proton into a neutron or a neutron into a proton. So, for example, if you have a case like this line here, where I put in a line to guide the eye, mass 3, that's got in this case, 1 proton, 2 neutrons. Helium-3, which has 2 protons, 1 neutron. They're the same number of nucleons, but they have a different number of protons and neutrons. Over time, they can change from one to the other. And so, in fact, if you take helium-3, it's stable. But if you take tritium, with a half-life of about 12 years, the tritium will convert into helium-3. And over here, I hope you can read this, you can see that some of these isotopes are stable. They're gray on this plot. And some of them are not. They're unstable. Now, if we work our way out from stability, let's look at the lithium isotopes. Lithium-6 and lithium-7 are stable. Go out to lithium-8, has a half-life of just under a second. Lithium-9, a fifth of a second. Lithium-11, a hundredth of a second. And lithium-11 actually is the poster child of isotopes because it has an amazing nuclear structure. When we come out on this side, and we're looking at things now which are, I'm sorry, I have to go back again, both far from stability and have very short half-lives. They're both difficult to make, and they don't stay around very long. And this is what we call a rare isotope. So for the purposes of the rest of the talk, this is my introduction to the table of isotopes. And the rare ones are the ones out here that are produced, live very briefly, die away. But on the nuclear scale, it's a very long time. And so their nuclear structure is well developed, and we can study it. There are basically 3 ways we can make them. There are others, but these are key ones. The first one is by adding neutrons. The second is by combining nuclei. And the third one, which is the one that we do here or we'll do at the FRIB and is done at the NSCL, is to shatter larger nuclei. So let's go back to the plot again and discuss that a little bit. Adding neutrons means that you'd start, for example, with hydrogen, add a neutron, move off to the left. Where would we find neutrons? Well, you can find neutrons in nuclear reactors. You can find neutrons in certain parts of the universe. Dr. Moses' new facility in Livermore, the National Glisson facility, is another place where you would find neutrons. But it's difficult with neutrons to make these nuclei out here because you have these gaps. Basically, as you work out, you can add neutrons to move to the right, then you hit a gap, and then you're stuck. You can't get to the furthermost ones. The second method that I had on that previous slide was to add nuclei together. That is an effective method. It's one that's been used by nuclear physicists ever since Ernest Lawrence invented the cyclotron 70 years ago. But what that typically tends to do is you take a nucleus, for example, like helium-3, add it to helium-4. That'll take you up to here, beryllium-7. So combining nuclei together takes us up at an angle. Again, it's a poor way to make the nuclei out here far to the right. The third method was to say that we can make these smaller isotopes by breaking up larger nuclei. And that's the technique that is used here at the NSCL. So, for example, you take a nucleus up here somewhere. That contains all the isotopes down below and to the left. So if we take that nucleus, perhaps hit it with a hammer, it's like hitting maybe a glass ball or something like that with the analogy. You look at the pieces, occasionally you'll find all the isotopes that are available below and to the left. And that's actually the technique and the experiments that Conrad and I and Gary Westphal and others did 30 years ago at the Bevatron for the first time.